Hello friends, in this video I'm going to answer to the questions which were asked in 2023 of moving charge and magnetism AHS second year final examination 2023, okay, under Assam Higher Secondary Education Council. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. that's my Insta ID. You can follow me on Insta as well. Okay, so now let's start. So here you see, this is the first question: match the following and rewrite. So here we have to match this with these sides. Okay, so here you can see this first one is QVB sine theta. Okay, so we know that when a charged particle enters a magnetic field, okay, in the direction perpendicular to the magnetic field, right, in the direction perpendicular to the magnetic field, and in that case, you know, this magnetic field exerts on this charge, exerts force on this charge, right, and that force is given by, if the velocity of that charge is v, then it is given by F is equal to V cross B into Q. That means the charge, right, into Q. Let me write it properly. F is equal to U into V cross B. And if you write this in scalar form, then F is equal to V cross B means VB sine theta, right, VB sine theta. And direction, when you have cross product here, VB, okay, and direction of the force will be perpendicular to both V and B because there is cross product, right? And in scalar form you can write this way. Okay, so here you see, so that's why we can say this F is equal to this expression. So that's why I have written here. Okay, now if you see, this is nothing but the Lorentz force. F is equal to Q E plus V cross B, right, V cross B. Okay, so this is the expression for Lorentz force. Here they are writing R vector within bracket. Means what does it mean? This is magnetic field at position R, this is electric field at position R. Okay, that's it. So this option is this is equal to this expression, right? So this one. So next you see, when a charged particle enters a magnetic field in the direction perpendicular to the magnetic field, after entering this magnetic field it takes a circular path, right, and radius of that path is given by this expression, mv by qb. Okay, so this r is equal to this, and you know the Biot-Savart law, this magnetic field dv is equal to this, so this is nothing but Biot-Savart law, right? So now let me take the next question. So here we need to calculate the value of mu naught by 4 pi and write its unit. So it is very simple. So you must remember that what is the value of mu naught for that, and divide it by 4 pi. Then 4 pi cancels, so you're gonna get 10 to the power minus 7 only. Okay, and this is its SI unit, or you can write this one as well. Okay, so that's it. Now in this question, a current of 0.4 ampere flowing through a coil of radius 8 centimeter and having 100 number of turns. Okay, find the magnetic field at the center. Now you see, due to a circular loop, magnetic field at a distance x on its axis, which is perpendicular to the coil and passing through the center of the coil, that is given by B is equal to mu naught by 4 pi. If there are n number of turns, then ni 2 pi r square plus x square whole to the power 3 by 2, and here we need r square. Okay, right? Now you see, but at the center, you know, x is equal to 0. So that means when this x is equal to 0, then we are taking this point. Okay, so now you see, for x is equal to 0, what we will get, if you put 0 here, then b is equal to mu naught by 4 pi ni 2 pi r square, that's going to be r square plus 0 square and whole to the power 3 by 2. So that means r cube, it becomes r cube, right? And r square cancels r cube to give r. Okay, and one more thing, remember that, so it is not necessary that in your book this the formula will be given in this form. Okay, it may be given in this way also. 2 pi cancels 4 pi, so here 2. Okay, so but I prefer this form because we can easily replace this one by 10 to the power minus 7, right? So hope you have understood this. So that's why I have used this formula here, and I put this given values here. So this is r, radius is given, this one is the radius, and 2 pi, 2 into 3.14 here, 2 into 3.14. okay, so 2 cancels 8 to give 4, and 4 cancels 3.14 to give 0.785, and if you multiply 100, 0.4 and 0.785, then it gives 3.14. And if you divide 10 to the power 7 by 10 to the power minus 2, then it gives 10 to the power minus 5. And if you write this decimal here, then it will be 3.14 into 10 to the power minus 4 Tesla. This is the required answer. So hope you have understood this. Parallel straight conductor A and B. Suppose we have two parallel conductors A and B. Okay, carrying current 8.0 ampere. 8.0 ampere current is being carried by this conductor A, and 5.0 ampere current is being carried by the conductor B in the same direction. Okay, they carry current in the same direction, and A and B are separated by a distance of 4.0 centimeter. That means 4 centimeter, you can say simply. Okay, so the separation is 4 centimeter. Okay, and current through this conductor A is, let me take IA, and this is IB. These are the information given here, and we need to find the force on 10 centimeter portion of wire A. So we need to find a force exerted on wire A, not on the whole wire, only on 10 centimeter portion, right? Now let me take a new slide and let me solve this. So we know that force exerted by these two wires on each other per unit length is given by mu naught by 4 pi 2 into IB. That means current carried by conductor B. Let me first write IA, then IB. Okay, current carried by conductor A and B, A and IB, right? By D, and here we need to find a force acting on 10 centimeter portion of this conductor A. So this L will be equal to 10 centimeter here. So now we need to find a force. So this L will be multiplied to this expression. So you can write this expression this way also, mu naught by 2 pi IAIB by D, but as I have already told you earlier that it is easy to put this value, right? Value of mu naught by 4 pi. So that's why I used to keep this expression this way, instead of cancelling this 4 by 2, right? So formula is mu naught by 4 pi 2 IA and IB by D into L. Here L is 10 centimeter, right? And currents are given here. Separation between the two wires D, that is equal to 4.0 centimeter, that means 4 centimeter, right? So use this value in this formula, then you will get this answer, 2 into 10 to the power minus 5, right? So hope you have understood this. So now let me take the next question. So our next question is, derive the expression for the magnetic field at a point on the axis of a circular current loop. Also find the magnetic field at the center of the loop. So here you see this is a current carrying loop, okay, circular loop, and we need to find the magnetic field at a point P, which is on the axis of this loop. Axis means the line which is passing through the center of this circular loop and perpendicular to the plane of the loop, right? That is the axis. So we have a point P on its axis, and we need to find the magnetic field at this point. Okay, just pause the video and note these things what I have written here. First note these things. Okay, so here I have taken an element xy, very small length element of this loop xy, which is dl, length is dl. So I have taken this as a vector quantity dl, okay, whose direction is is actually out of the screen. Okay, you will take the note later. First let me explain. Suppose we have a coil, circular current carrying loop. Suppose this is a circular current carrying loop. So I current is flowing through this loop this way, okay, and let me take this is the axis of this loop, okay, and we need to find the magnetic field at this point P, okay, at this point P due to this loop. And first let me take a very small length element, this is dl suppose, and its direction is towards this along the direction of current. So here at this portion direction of current is this, okay, so in the same direction of current I have taken the direction of dl. So let me write this one as dl vector, and its radius is suppose capital R, and distance from this element to the point P is suppose small r, and if we consider the position, this is as position vector of P with respect to dl, then we can write this in vector form, okay. And let me take this distance between the distance between the center and point P, where I need to find the magnetic field, is suppose x, okay. Now this direction of dl is not along this direction. This is this is the display of your device where you are watching this video, and half of the coil is out of the device and half of the coil is inside the device, and the plane of the coil is perpendicular to display, you can consider that way. So this is the the display of your mobile or tablet, wherever you are watching this video, and the coil is on a plane. This is the plane of the coil, and which is perpendicular to the display of your device, consider that way. And in that case the direction of dl will be this. This is the direction of dl, which is out of the screen, So hope you can imagine this, okay. This is out of the screen, okay. So now we know that according to Biot-Savart law, this is a conductor and this is a very small element dl, and suppose we need to find a magnetic field at a point P due to this element, that is given by dB is equal to, if you write this in vector form, then it's given by mu naught by 4 pi I dl cross r vector by r cube. Hope you know this. And if you write in scalar form, so magnitude of dl cross r is dl r sin theta, and if you cancel this r cube by r, then it's gonna give you r square, right? So we will get this, okay. This is in scalar form, okay. So now this theta is the angle between this r vector and dl, that is theta, right? So here the direction of dl is this, suppose, and this is the direction of r vector, and angle between these two is theta. But in this case this dl is perpendicular to this r vector, okay. So DL is in this direction, which is perpendicular to your screen of the device where you are watching this video, which is out of the device, out of the screen, and this is the R vector which is on the plane of screen, which is on the screen. Okay, so these two are perpendicular, so here we're gonna put 90 degree here in this case, right? It's gonna be 90 degree. Therefore magnetic field due to this small element DL, so therefore magnetic field at this point P due to this DL, so according to this expression, magnetic field at, now don't write all these things, I will give you the note at the end of this video. I will show you the slides where you can see the handwritten notes. Okay, you will note it after this explanation. First let me explain this. Okay, magnetic field at P due to DL according to Biot-Savart law will be dB is equal to, so in scalar form, dB is equal to mu naught by 4 pi I dl. Here it will be sin 90 instead of theta. Here the angle between this dl and r is 90, as I have already explained how it is 90, right? So it's going to be r square, and this is going to give you mu naught by 4 pi sin 90 is 1, so I dl by r square. That's what we have got. And the direction of, so here you see we have dl cross r, that means direction of dB is perpendicular to both r vector and dl vector. So now you see, so cross product of dl, two vectors dl cross r, that always, so this is suppose dl, this is suppose r, this is dl, this is suppose r, then direction of dl cross r must be perpendicular to both r and dl, right? Hope you know these things. So here dB is perpendicular to this as well as this direction also, perpendicular to dl as well, right? Hope you have understood this. So now you see, so it can be resolved into two components. So let me take this is perpendicular, this is this angle is supposed theta, and here you see this is perpendicular to r vector, right? And this is perpendicular to this axis. So if the angle between their perpendiculars is theta, then this two angle between these two also must be these two must be theta, because hope you know, if you have two lines, suppose angle between them is theta, then if you draw perpendicular to these two lines, this one is the perpendicular to this line, and if you draw a perpendicular to this line, then the angle between their perpendiculars must be same as angle between these two lines. Hope you have understood this. So now you see, so dB can be resolved into dB cos theta. dB cos theta, if this angle is theta, then this is dB cos theta. Okay, so this is perpendicular to axis of the coil, right? And another component is dB sin theta, that is along the axis of the coil, along this direction, dB sin theta. Okay, along the axis of the coil, right? Now you see, as you can see, this element dl, as this coil is symmetric about the axis, so if this element dl is here, then if you draw a diameter here, and on the other side of the coil you will on the other end of the diameter you will get another dl component, and where you see this dl is taken in this direction where in which current is flowing, right? Now current is flowing in this direction, and at this portion the direction of the current will be in this direction, in the direction that is into the page. Okay, not this, I am not saying this in this direction, this is into the page. Okay, this is out of the page, Okay, this is into the page. That means out of the page means this is generally represented by dot, into the page represented by cross, right? Hope you have understood this. That means it is perpendicularly, it is going into the page normal in a direction perpendicular to the display where you are watching the video. Okay, so hope you have understood this. And as here direction is opposite, that's why magnetic field due to this DL component will be along this direction, and its perpendicular component will be along this direction, dB cos theta, which will be equal and opposite to this component, and these two will cancel each other. Similarly, for each and every DL element of this coil, there will be an equal and opposite element DL on the other side of the diameter of this coil. Okay, and due to those, magnetic field due to those will be such that their perpendicular components will cancel out. Okay, now if you consider these two elements, then suppose it's a magnetic field due to this element is suppose in this direction, so it will also have perpendicular components to this axis, and one is horizontal component, and similarly due to this one will be in this direction, suppose it will also have perpendicular components. Okay, and the perpendicular components will cancel out. Perpendicular components of dB due to this and this due to this element will be equal and opposite. This is the axis, both are perpendicular to the axis, then these two will cancel, right? So similarly, if you take an DL element here, so and if you draw a diameter, and on the other side you will get another DL which is equal to this but opposite in direction, right? So that's why all the perpendicular components will cancel out, and the horizontal components will add up to give the resultant magnetic field at the point P, right? Hope you have understood this. So magnetic field at P due to the loop will be given by vector B is equal to let me write the scalar form first. Okay, so B will be given by if you add up all the B sin theta components, so sorry, here no vector sign. Okay, dB sin theta components, if you add up all dB sin theta components, right, then you will get the magnetic field at P. So here it can be written integration dB sin theta. Now let us replace this dB by this result, by this expression. Okay, then what you gonna have? Integration mu naught by 4 pi I dl divided by r square and sin theta. This part is replaced by this expression, right? Hope you have understood this. Now you see here this part is constant, only we can keep the dl. Here you see we can rearrange this term like this way. Just give me a second, let me cut these two steps. Okay, so it can be written this way now: mu naught by 4 pi I sin theta by r square integration dl. That's what we have got, right? Hope you have understood this. So now integration dl means the circumference of this circular loop. Okay, so this dl is nothing but integration dl. This integration dl is equal to circumference of this loop. It will be given by 2 pi, capital R is the radius here, so 2 pi r. So that's why this expression will be of this form: mu naught 4 pi I sin theta by small r square, then 2 pi capital R. Now this sin theta, let me cut it. This sin theta can be replaced by, here you see, if you see this triangle, here this perpendicular is R, right? In this triangle, this r is the perpendicular, and this length small r is the hypotenuse. Okay, so from this triangle, here it is theta, this is capital R, this is small r, so sine theta will be equal to perpendicular by hypotenuse capital R by small r here. So that's why let me replace this sine theta by capital R by small r, then this equation of this form, let me show you, then it becomes mu naught I 2 pi r square divided by 4 pi small r cube, right? That's what we're gonna have. So if you want to cut this 2 pi and 2 4, you can cancel, but I would like to suggest don't cut this, because in case of numerical, when you want to solve numerical, then we know it is easy to remember this value of this part is 10 to the power minus 7, right? So it becomes easier to do the calculations. So that's why I used to keep in this form. Okay, so now you see, from this triangle we know this distance is x, and if you apply the Pythagoras theorem, then small r will be equal to root over capital R square plus x square using Pythagoras theorem, right? So we can replace this r cube by this. So if you replace that, what you will get? For first, let me clean these things. Okay, so now what we have got b is equal to mu naught I 2 pi capital R square by 4 pi r cube. Now let me clean all these things so that I can explain. Okay, now this, from this triangle, this is capital R, small r, this is theta, this is x. So using Pythagoras theorem, r square will be equal to capital R square plus x square. So r will be equal to root over r square plus x square, or you can say r square plus x square whole to the power half, r square plus x square whole to the power half. And if you take r cube, then here half into 3, that's gonna be equal to, so this r cube will be replaced by r square plus x square whole to the power 3 by 2, right? Hope you have understood this. So this is the expression of magnetic field at a point P on the axis of a circular loop, right? And if you want to cut this, you can cancel. Okay, you can write this way also, mu naught I r square by 2 r square x square whole to the power 3 by 2. Okay, and this coil, if it consists n number of turns, capital N number of turns, then this then you have to multiply capital N here. Okay, if there is a single turn, then this will be the expression for n number of turns, n turns. This expression will be of this form, mu naught I n2 pi capital R square by 4 pi capital R square plus x square whole to the power 3 by 2. And if you cancel this 2 pi and 4 pi, then here you're gonna get 2. Okay, and you can write this expression in this form as well, or you can write this in this form as well. Okay, so hope you have understood this. Now if you find the magnetic field at the center here, in that case x will be equal to 0. If you bring the P here at the center, then x will be equal to 0. So at the center, if there is only one turn, then put 0 here. Then this at the center O, this expression will be equal to mu naught I capital R square by 2 R square to the power 3 by 2 if you put x is equal to 0, right? So 2 cancels, so we're gonna end up getting, here we end up getting r cube. So here r square cancels r cube to give r only, so that's what we will get. And for n number of turns, again you need to multiply here n. Okay, hope you have understood this. Now take the notes, let me show you. So just note it from here. This is the first piece, pause the video and note it, and this is the second. Okay, pause the video and note it. Hope it is clear to you, distinctly visible, I think, right? So now this is the next piece. Take the screenshot, or you can note it if you want to write. This is the last piece. Okay, so these are the expressions. So I have written the expressions for n number of turns here, n number of turns here. Okay, so for n number of turns, these are the expressions. So hope you have understood this. Thank you for watching. See you in the next video. In the next video, I'm going to solve the I'm going to answer the questions of this same chapter which were asked in 2022. Okay, in AHS second year final examination under Assam Higher Secondary Education Council. Okay, so see you in the next video.